Hello, this is the my circuit board for the line tracker project. And I will go through what each part is, and I guess like the color coding as well. It's just like there's a slight color coding, and then we can go through all the states. All right, so here in the corner, actually here in this corner right here is the timer. Um, this is just a 555 timer. Um, I I made the clock speed slower for because it'll be easier to see. Generally, the clock speed for here would be for the register uh, that's in charge of the main FSM will be faster, and the register for the clock speed for the factored FSM part would be slower. But those would be found out through um, experimental runs. Over here, we have the register um, with T1 and then T naught over here. And of course, the outputs of these registers will be plugged in to the different and or statements that are used to construct the next state. Further down, we have an inverter. This inverter is mainly to uh, create the equations that were derived from the state transition diagram. Also, these three buttons are the outputs. No, the inputs. Um, Normally, we have 8 inputs, and I would group them with AND gates. However, for the sake of practicality, P1, P2 is this button, P3, P4 is this button, and P5, P6 is this button. I'm just going to move to the a diagram of what the photodiodes would be. So the leftmost photodiodes are P1 and P2. Then the middle 4 are P3, P4, P5, 6, P6. And P7 and P8 are the rightmost. However, in my logic, we are not using P7, P8. We're only using these 6 photodiodes, and therefore these 3 combinations. Moving back here, I had this resistor set up and the wire set up just so that it will be an inverter button where the initial output of the button when it's not pressed is a 1, while when it is pressed it's a 0. The main thing down here is pretty much the FSM that is going to count. Well, it's going to keep track of the intersections. So, this is what's that? Here is the AND gates that are used for the factored FSM. The secondary FSM part, while the OR gate is over here, and there's a separate register for just for the sake of convenience and so that there's less wires, spanning the entire circuit board. And these are the outputs. So this LED is the output of this button, and this LED is the output of this FSM. This will make sense a lot more when we run through the sample cases. Right in the middle, this is the combinations of all of all the equations that are used to derive the next state. I mainly did it. A lot of these were 5-term. I think the lowest amount of terms were 3 terms. So I would here's how the equations looked for T1 naught and T1 prime and T naught prime, which is the next state logic. Pretty much anything in red are initial inputs, like our separate inputs, while anything in green are combined inputs. For example, the red wires coming out are the S1. The T1 and T naught, as well as their bar values. So like This would be like T1. This would be T1 not. This would be T0, and this would be this would be T0 not, and this would be T0. Anything that gets combined, or anything that's like data, is gonna be in green, while everything that's related to power is yellow. As you can see, like the yellow is connected to all the VCCs and the grounds, and the yellow also connects all the power lines together, so the power is distributed all from this power supply throughout the circuit board. I would go over all the connections, but frankly, the terms are kind of a little bit long, so I'll just do a practical demonstration of the states. Oh, and actually, this is the OR gate responsible for the outputs. Actually, yeah, the OR gates. The equations for the outputs are actually on this page. They're on the top part, so pretty much anything addition related is OR, and anything multiplication related is AND. However, I was able to simplify all the output equations to two terms, or even just like a value. Alright, so let's get started. So, when we turn on the, hold on, I forgot to reset this. So, when we turn on the circuit, we automatically see that these 8 LEDs are lit up, and this is just a timer. So these 4 LEDs over here represent the left motor power, and these over here represent right motor power. So currently it's at a default state where it's just running straight. This is the first state that this line tracker will probably run through. So while we're holding these two buttons, right? We're holding these two buttons, P34 and P56. Because we're holding them, that means that they are on the line, because as I said before, these are inverted buttons, so right now it's outputting a 0. And so as you can see, in accordance with the simulation, both left and right motor powers are in their highest power. Next, we should test the right state. So when it's gonna move, when the track bends to the right, P34 becomes a 1. So let's let go of that. And as you can see, the power on the left has dropped by half, while the power on the right stays the same, simulating the fact that the tracker will move on more of a right curve. And now when we get back on the line, right, that's when P34 is a 0. So when you press the button, everything's back in the straight states. Next, we want to test the left state. So when the track is bending towards the left, P56 is going to become 1, because P56 will be off the line. So we let go of that, and as you can see, the power becomes halved on the right side, and the power on the left kind of stays in full power, suggesting that the tracker will end up moving more to the left side to keep up with the left bend. And likewise, you press the button again, and you get back to the straight states. Now, here's where this factor of some comes into play. So, when we track an intersection by checking the what the photodiodes 1 and 2 are inputting, which is this button right here. Just as a refresher, this is P12, P34, P56. So this is the ANDed version of photodiodes 1 and 2, ANDed version of photodiodes 3 and 4, ANDed version of the photodiodes 5 and 6. So if the line tracker PCB were to be functional, we'd have the instead of these 3 buttons, we would have the photodiodes from 1 and 2 connecting onto the circuit board and AND it together. with the AND gates, and likewise with 3, 4, and 5, 6. Anyways, going back to why this factor FSM is important, pretty much, this factors FSM is supposed to save the whether it's the first or second intersection that we've crossed. So because initially this y output is going to start at 0, and once we cross that, so let's say we're going straight and then we cross it, this button over here is going to simulate the clock speed. Because we didn't get to do enough like experimental testing, the clocks we don't know the actual value of the clock speed, so we're going to use this button to simulate it. So we hold these 3 buttons here, and then we hold this button down. Oh, this is actually kind of tough. Let me use this hand. All right, so 3 buttons here, and as you can see, when we turn that on, and then we let go of the. So this means that we're on the this red you see means that the FSM has registered that this is the first intersection that we've crossed. Of course, the blue one represents the fact that this button's being pressed. So if I can just move to the how the LEDs look, as you can see, all the power is being directed to the left motor because we want to make a hard left turn. So there's absolutely no power being distributed to the right motor power. Now, when we let go of this button, we can see that the right button, while it was turned off before, is now turned back on. Well, now it stays on even after the button is pressed, and that's because this factor FSM is now saving the fact that this is the first intersection that we've crossed. So when we similarly to what the simulation was like, and as long as we let go of P12, which means that P12 will turn back to 1, which means that the tracker, the P12 node, the P12 photodiode is no longer on the line. When we let that go, we move to either a straight state, a left state, or a right state, depending on depending on how the P34 and P56 outputs are, and we continue with our normal deal. So it's at a straight state, and then we let go of that. It's in the right state. We put that back. It goes straight again, and we let this go, and now it's on the left state. And then we come across intersection again, right? So we're moving straight, and we come across intersection. Ideally, this button down here, the clock for the for the YFSM will coincide with the intersection, and we would oh, hold on. So, and then we would have it so that the Y is turned off. So now we let go of P12. And as you can see, we're now in a safe state. So even if we press P1, we're in the Y equals 0 state. So even when you press P1, nothing really happens. It just goes straight. This is how I made sure that on the second time the line tracker reaches the intersection, that it would just keep on going straight. And as you can see, I'm pressing this down, and absolutely nothing's happening. It's just going straight. And then we move on with the same states. So we let go of this, and we let go of the P56. It turns left. We put that back on. It goes straight, and we let go of P34, and it just turns right. And then at that point, we will reach the finish line. So that is it for my circuit board. This was an interesting project, and it's quite a bummer that we couldn't really test it. But Anyways, it was a quite an experience, and thank you for letting me work on this project.